Suppose I give you an object and asked you to find its mass. What would you do? Well, the first thing that would come into your mind would be to use a weighing machine. This machine will give you some reading, say 5 kg. This reading is actually the weight of the object, but not its mass. Weight is the gravitational force of the earth on the object, which is mg, mass into acceleration due to gravity. From this we get the mass of the object as W by g. But as the acceleration due to gravity g is same for all objects at a place on earth, therefore weight becomes directly proportional to the mass of the object. Hence in this case you also get the mass of the object as 5 kg. But what if I go ahead and ask you to find mass of something huge such as a rock, lake, ocean, weight, mass of the entire earth? Yes, the topic of this video is how do you calculate mass of our planet? Well, this task of estimating mass of our planet had been undertaken since ancient times. Astronomers and mathematicians of the ancient world became aware of the fact that Earth was a huge spherical object around which the heavens revolved. They even tried to guess its volume and density. From there, they estimated its mass by multiplying density and volume. However, they got wrong answer due to the fact that they had no idea of Earth's interior, and hence the wrong result for both its density and mass followed. The real solution to the problem of finding Earth's mass became possible only after 16th century with the advent of Sir Isaac Newton and with the discovery of universal gravitation. This discovery of gravity enabled us to not just calculate mass of Earth but also mass of other planets in our solar system, mass of sun, mass of stars, galaxies, nebulas, clusters, etc. So according to Newton's law of gravity, every particle of mass attracts every other particle of mass with a force that is directly proportional to the product of masses and inversely proportional to the square of distance between them. So F is equal to g m1 m2 by r square, where m1 and m2 are the two masses, r is the distance between them, and g is the universal gravitational constant whose value is 6.67 into 10 to the power of minus 11 Newton meter square per kg square. So this equation of gravity is something which most of the students of physics are basically aware of. So using this equation we can find mass of celestial objects, and in this case mass of Earth. If you are somehow able to measure the gravitational force between two masses and know the distance between them, and if they are large objects, distance between their centers, especially spherical masses, the distance between their centers, and also value of one of the masses, we can find the value of unknown mass. So in our case the unknown mass will be mass of our Earth, which needed to be found out. So for that, consider any arbitrary mass on Earth's surface, say m. It can be any object. The weight of this mass is the Earth's gravitational force acting on it, which is mg. This is something which most of us know. W is equal to mg, which in turn equal to g into m into me by r square. So this is the crucial step to finding out Earth's mass. W is equal to mg, which we all know, in turn equal to g m me by r square, where r is the distance between both the objects. But as the small mass m is negligibly small compared to the size of Earth, its size can be neglected. So the distance between the two objects is simply radius of the Earth, as the object is lying on Earth's surface. From that you get g is equal to g me by r square, And finally, expression to calculate mass of Earth, we got it. ME is equal to g r square by capital G, where small g is the acceleration due to gravity, r is the radius of Earth, and capital G is the universal gravitational constant. The value of these three constants most of us know as they're in textbooks. So by substituting, you get the mass of Earth. But wait, let us see how did scientists find out values of these three constants. So acceleration due to gravity g can be obtained by simply dropping an object from a known height h and recording its time of fall t. From that you get a simple kinematic equation, which is h is equal to ut plus half at square. Initial velocity 0, h is equal to half gt square, because acceleration is the acceleration due to gravity, which we need to find out. From that you get g is equal to 2h by t square. Value of h you know and time of fall you know. Substituting, you get g as approximately 9.8 meter per second square. Now comes the radius of the Earth. Radius of the Earth can be found out using simple geometry. So this was the technique used more than 2000 years ago by ancient astronomers to accurately calculate the radius of Earth without any instruments. So for this, we need two separate locations on Earth's surface. From two locations on Earth's surface, there is an apparent shift in the position of a distant cosmic object such as Sun. This angular shift can be measured, and if we know the distance between the two places, we can accurately find out radius of the Earth using simple proportionality. This was a method used by Eratosthenes, a Greek astronomer, to accurately measure radius of Earth more than 2000 years ago. So you can see that at two separate locations, the observer sees the Sun at different angles in the sky. So if the separation between the two persons is s and the angular shift in the position of the Sun in the sky is theta, the same theta is the angle between the two radii, OA and OB. So we get that from simple proportionality, S by C, C is the circumference of the Earth, which we assume we don't know, and S is the distance between the two locations, which is measurable. So S by C is equal to theta by 2 pi, simple proportionality. So the ratio of the arc lengths is equal to ratio of the angles subtending them at the center of the circle. So you get C is equal to 2 pi s by theta, and from that you get R is equal to s by theta. So in one stroke you get the circumference as well as the radius of the Earth. So assume the distance between the two locations is 1000 kilometers, and the angular shift of the Sun observed is usually of the order of 0.156 in radians. So dividing 1000 by 0.156, you get the radius of the Earth as approximately 6400 kilometers. Now to calculate the third constant, that is g. Calculating gravitational constant g is a bit challenging because gravity itself is a very weak force, but it can be done. In fact, around 17th century, a physicist known as Henry Cavendish accurately found out the value of g using a simple torsion balance. So the gravitational constant g can be found out by developing a simple torsion balance that responds to gravity by turning through a very small angle theta that can be measured by careful observation. The equipment consists of a horizontal bar as shown in the figure that has two identical masses attached to either ends. This bar is suspended horizontally from a wire and it is in the equilibrium position originally. Now two identical but heavier masses are brought close to the original light masses. So the gravity between the smaller lighter masses m and the heavier mass m on the either side, on both the sides, cause the bar to deflect through a very small angle, and using the torque equation we can calculate g. G turns out to be 6.67 into 10 to the power of minus 11. So simple torque equation, tau is equal to k theta. But torque is force into perpendicular distance. There are two forces, gravitational forces on the either side of the center, so which amounts to 2f. 2f into perpendicular distance is half of the length of the bar, which is L by 2. So 2f into L by 2 is equal to k theta. What is f? G m1 m2 by r square. So 1m is small m, other one is capital M. So G small m into capital M by d is the distance between the masses. So G mm by d square into L is equal to k theta, from which you get the value of G. If the experiment is conducted carefully, you get the value of G as 6.6743 into 10 to the power of minus 11. So from this you got the values of the three constants. So substituting in the mass expression of the earth, you get mass of the earth. So G is 9.8. Radius of the earth is obtained in kilometers. Convert into meters. 6,400 into 1000 whole square, and universal gravitational constant as 6.67 into 10 to the power of minus 11. Using a calculator, you can get the mass of earth as approximately 5.97 into 10 to the power of 24 kg. That's all. This is a small but challenging problem to calculate mass of earth. Thank you.